All right, so we will kick off with our final session of the course. All right. Yeah, so welcome folks. Last session of the course. We've already had all of the content as discussed. The last lecture was the main lecture or the final lecture, and no kind of big long spiel from me today. One of the things, well, so I discussed last time, I kind of threatened to give you a few highlights of review, and I'm going to do that briefly and comment on one or two other things that were asked about kind of resources. So just a few minutes of some miscellaneous kind of wrap up review comments for me to kick off. Then I'm going to kind of sequester you to do the evaluation form because we need those completed. The link is in the Zoom already. That anyone who, yeah, I guess maybe Andrew, if you can grab it from the Zoom chat, and Mina Rose, that will probably be the easiest. And then we'll get into the presentations. So, and that's the main job for today. So thank you everyone, here on the call and those who are following offline for submitting your presentations, your assignments and your presentations. So we've had some great content come in, you guys, answering the questions, but like exploring the computational content in the notebooks and giving us your recordings. So today the plan is as follows. We have a few people in the room, a few people online. Maybe we'll have some more people join, maybe not, but we're going to have those in the room and online. So just sharing you right now, we're going to kind of have you give your presentation live. And there, the job is to stay on time. Okay, so the way we're going to kind of enforce that is just start the clock, but I basically indicate when you're nearly at time. When you're 1 minute from time, at least Andrew, I'll wave my little booklet. So you have a bit of a warning. Shirin, a little bit harder for us to do that for you. Maybe we can do it with a message on the chat, but just be mindful not to go over time. That's kind of the key thing. And then we have several recordings as well from submitted things. So we'll play those as well. And we're evaluating them, right? So this is like a part of your grade is your presentation today, and those who've sent it in who would play, we're kind of some of them at least we're watching for the first time, so we'll be grading them as we go as well. But it's also going to be interesting to see what people have to say. So that's the plan for today. It's mostly driven by you. If there's any questions on any of that, happy to take them now. No, all good. Okay, so let me just say one or two things in review. I had this spiel all the way through, so I'm just going to kind of come back to it because to some extent this was this kind of covered. This does represent the content and some of the consistent themes that we talked about in the course. So let me just kind of wind this back in case people forget what the spiel was for this slide. Okay, so the things I said when I introduced this in the first lectures: computational neuroscience, substitute mathematical neuroscience. That's the name of the course that we're doing here, but computational neuroscience may be a bit more of a widely used term. Is a broad church. As I described, it's kind of larger. It's like the entire field of neuroscience, and then a kind of slice of a good number of other fields. So it's like bigger than neuroscience to some extent as a field. Broadly speaking, though, we've got two main kind of classes of content and ideas that are covered, right? Things about relating to cognition, information processing, representation, coding, and things related to, if you like, physiology, but particularly aspects of physiology we can characterize in terms of dynamics. And most of the stuff that we've covered in the course has been over here, but some of it has been over here. A few more comments on that in a second. And as I indicated when I gave this in the first lecture, is that down the middle, we have like, say, work or ideas, concepts that are kind of spanning the two. So still having some aspect of describing the dynamics and the physiology of neural systems, whilst also speaking to something about representation, computation, information processing. And, you know, doing both of those things, in my opinion, at least, is the holy grail of computational neuroscience. And it's not easy, but it's to some extent like the most impressive and rewarding work is when, you know, you see people you see new science that is having like a little bit of this and a little bit of this. But yeah, in terms of the course, right? So we had, I didn't include my other kind of regular figure, which is the journey up the spatial scales, but we had that at the beginning of every lecture. And, you know, most of that kind of going up from the micro scale to the macro scale in terms of the physiology and the biology, from cells to patches of tissue to networks to large scale brain activity and connectomes and so on, is kind of just naturally falls in the right hand side of the slide here, right? It kind of naturally is just things that we think about in physiology are kind of they tend to be biophysics type things or time series type things or dynamics type things. So to some extent, you know, the part of the course, the theme of the course where we were just moving up the spatial scales, I think is, and I've even got it on the slide here, right at the bottom right, it is mainly a feature of the right-hand side of my kind of sketch here. However, you know, we dipped into the left-hand side a few times, right? If you recall, like we lecture 2 or lecture 3, we kind of segued quite a bit when we went into we talked about Hopfield networks, but not entirely, right? So the Hopfield network kind of structure is a you know, it has elements of brain network organization in it, like all artificial neural networks do, but it's not really a description of neurophysiology. It's a description of like ideas about how memories are stored, right? Oh, excuse me. How memories are stored and how kind of information processing might work in like network structures, and recall and phenomena like that. But what we also did in that lecture was we kind of implemented the kind of structure of the pattern learning in Hopfield networks in a spiking network, right? So kind of to some extent kind of started to cross this holy grail explanatory gap a little bit with the tutorial example. So it was in the notebook, you know, good job Parza for pulling that together, that was kind of doing Hopfield network stuff with spikes. So that would be a kind of concrete example of the kind of thing I'm talking about, that's, say, bridging a bit of physiology and a little bit of representation and information processing oriented computational neuroscience. I think some of the stuff that we covered is kind of moving forward a few lectures in the probabilistic brain session, doing a similar thing there. So, you know, we talked about noise, but we also talked about a little bit about predictive coding. And to be honest, we could have talked more about predictive coding, but ideas about Bayesian brain, or kind of just the brains and cognition acting in terms of Bayesian inference and related stuff like that. So there again, like we were kind of moving around between here and here. But most of the most of the really, you know, recurring themes that we covered in the course, which were things like you know, stability analysis on dynamical systems, bifurcations, phase planes, oscillations, properties of networks, again, in this space on the right-hand side. So that's kind of what I would like to do. Didn't really have time to do it for today, but it is to sometimes to kind of take, say, all of the slide headings or the section headings from the course and just kind of drop them down on here. If we did that, I know for sure, like what you get is like a kind of point cloud, like density cloud, where, you know, we were like, we covered a lot of stuff spanning over here, and we had a few samples over here. And again, we had a few samples down the middle here. Now, other computational neuroscience courses you might do, and I absolutely encourage you to do that and like find, you know, explore other options. And this comes to my next and like final review comments here about additional materials and so on. You know, they might emphasize actually this side of things entirely and very little about this, or they might be all about this and nothing about this. Like there's a lot of variation in how people kind of pick a kind of menu to cover. And there's a lot of considerations why, right? Kind of interest, but also I mean, it's impossible to do everything, but like certain groups of things hang together well, say from this side to this side, and some don't. So I do feel like, broadly speaking, the kind of multi-scale neurophysiology, it just works quite well as a kind of anchor. And there's not really the equivalent on the left-hand side in terms of being able to kind of go progressively up from something that we can really put our finger on at, say, a, you know, cellular level of resolution and kind of moving up, you know. So I think to some extent the structure of the, you know, space of computational neuroscience with respect to information processing and coding is like a little bit less organized, right? Or kind of explicitly hierarchically structured than on this side, because this side basically follows anatomy, right? In the sense of like following spatial scales, right? It kind of follows the anatomical parts of and anatomical and physiological structures in the brain, and then we look at the dynamics like going on at those spatial scales, right? So, you know, this is something you'll find if you kind of do further reading and exploration, I think, is that there's like a lot going on in computational neuroscience of information processing and coding, but it's kind of not got very many like really coherent, say, umbrella or kind of like unifying threads. I mean, there are, but they're a little bit less organized. So there's some miscellaneous thoughts about some of the kind of cross-cutting topics from the last few weeks. Final two things I want to talk about. Yeah, list here. So this slide was in lecture 1, and there was a question, a kind of comment from the end of last lecture, which is like, can you, I think maybe it was from you, Shirin, which is, can you give some comments on resources and you know, future reading and so on? So yes, absolutely. And I'll just summarize some of the things I've got on the slides and just give a few comments as well, and then that's up for my wrap up here. So first thing is podcasts, and there's very few podcasts out there that are better than Brain Inspired. I'm just going to kind of state that. This has been running for a few years. To be honest, I think it might have been going before like the kind of AI boom, or at least insofar the kind of LLM stage of the AI boom. But this is just a really great, and it's hundreds of episodes now, but like it's looking for people doing interesting work that is at the intersection of neuroscience and AI. That's the kind of concept behind Brain Inspired. But there's a lot of interesting neuroscience in there. There's a lot of interesting AI. Like I've learned a lot about both neuroscience and ML that I knew nothing about, just kind of dropping into this podcast. So Brain Inspired, go to it, check it out. That's, I think, my #1 recommendation. Older ones, right? So this one, Neuroscientists Talk Shop, like I was listening to this when I was a grad student. So this kind of goes back a while, but similar thing, right? I mean, not AI, not ML, but really good interviews and kind of a high level, like in the weeds content, which is a good thing. Like I kind of prefer content that is extensive and deep and gets down to things rather than like survey, because that just obviously my bias. So Neuroscientists Talk Shop, check that out. There was one person who is involved in, I don't know if she was the like one of the organizers or just a regular guest or something, and then Grace Lindsay. I mean, I know the name Grace Lindsay because I heard Grace Lindsay on this podcast. But Grace Lindsay published a book a few years ago, and I mean, quite impressive, because I think she'd only just finished her PhD, so she must have written this like as a grad student or just shortly after. And this is a book that you can find in the bookstore, like in Indigo, in your regular bookstore, your neighborhood bookstore. It's like a popular science book, more or less about computational neuroscience. So I think this book models the mind. It's really good. It's one of the, and it's a little bit unusual to see a computational neuroscience book kind of featuring, which is just anywhere on the shelf, right, on your high street. You know, definitely big recommendation for that one. Other books, other books, I've got some more on the next slide. Podcasts, one or two others I want to mention, not all of them are on here. This is a cool one, Convergence Network, Science Network, a bit all over the place, but from a group in Spain, who just have a lot of interesting interviews and so on. People are into brain stimulation, which is a little bit outside of computational neuroscience, but there is a really, really good podcast called Stimulating Brains that Andy Horn has been running for a few years now. And that's like absolute gold if you're actually working on brain stimulation. I mean, if you're interested as well, but if you're working in brain stimulation, it's just mandatory listening. So Stimulating Brains. And yeah, one or two others I'm probably not remembering, but the final thing I want to mention on this slide now, extra resources, is this film, in silico. So this is a film about the Human Brain Project, that is not in a way the most complementary to the, if you like, institution of computational neuroscience. There was a lot of politics around the, I had to, should I even go into it now? Should I go into it? Go for it. All right, why not? Okay. In 2010, there was a, I want to say, €1 billion grant given to two large research consortia. So two like extremely large grants given to groups of scientists by the EU, by the European Union. One of them was about graphene, stuff like so biomaterials. You know, graphene, I think had like recently won the Nobel Prize, discovery of graphene. And the other went to this group called this project called the Human Brain Project. Now, the Human Brain Project was an evolution of another kind of research consortium, kind of research institute based in Switzerland called the Blue Brain Project, which was partly funded by IBM, but mainly by the Swiss government, and led by a fellow named Henry Markram. But it wasn't just that, but essentially it was like Henry Markram kind of taking Blue Brain, which was really focused on very detailed modeling, computational modeling of pieces of mice brains, rat brains, sorry, and then later on mice brains, and doing the same thing that Blue Brain did for rats in humans, hence the name Human Brain Project. I mean, that's the kind of implicit part of that. So in any case, like a lot of money went to this large, like dozens of groups all across Europe to do Human Brain Projects, but really with the figurehead and the centerpiece being this line of work coming from Blue Brain Project, doing super detailed modeling of the rats, what they've done in rats in humans. Okay, so then fast forward like 5 years, 2015, 2016 and so on, there was always grumblings around the fact that the EU had kind of given so much money to one project and therefore by necessity kind of not gone to other projects, other people working on other stuff. And the argument to some extent was like, there was a bit of a dearth of like theory, not so much theory in terms of like the maths, but like, what is the actual research question here? Or are we just trying to build big models? And that like resulted eventually in a kind of coup, where the lead guy, Markram, was kind of removed and the project took a different direction. So, and there were good things that then came out of that, some of which I'm indirectly involved in. But in any case, like Human Brain Project took a different turn halfway through because there was a coup and they basically removed their figurehead, right? Now, while this was all happening, this guy, Noah Hutton, was making a documentary about it. Initially because he was like, this is super interesting. But then I think the way that it went is like the documentary then kind of necessarily took on the theme of all of the political machinations and controversy that came up and swelled up and developed around the project, and that became to some extent the kind of narrative of the documentary. And to the extent that that is the narrative of this documentary, it's a bit of a shame because what's also going on behind all of the politics is like very good science. It's just very good science and politics, and it's hard to really feature science, you know, narratively as such. But no, in any case, like there is an interesting documentary. I think it debuted at TIFF, you know, so it's like but you can get it on YouTube. We did a screening for at our institute retreat a few years ago. That was fun. My old boss Sean Hill features in it, walking down the corridor in t-shirts, and then as he gets more serious, well, he gets promoted, he walks down the corridor in suits, but he looks exactly the same otherwise. And yeah, so In Silico is kind of fun documentary if you want to go there. And then books, and this is my final summary slide. So this one here, the second one, Diane and Abbott, okay, this is kind of the Bible still, Theoretical Neuroscience Bible, quite an old book, but this stuff doesn't really age that quickly. And so this has really been like the primary textbook of computational neuroscience courses for, I'd say like more than 20 years. And you could do worse than grabbing this book if you're interested in going deeper on more or less anything that we covered in this course. In terms of other stuff that we covered in this course, everything about spiking neurons, also up to kind of populations. There's several books by a very impressive scientist named Wolfram Gerstner, who's based in Switzerland. So this is one of them. He's got about 3. He's also got websites with lectures and content. And I would say, like, if you recall, like when I did the lecture on single neuron models, and I said you could do an entire course on just the like leading up to the formulation of the Hodgkin-Huxley equation, well, you can get that course from Wolfram Gerstner's website if you want to do like 10 lectures on Hodgkin-Huxley rather than 1. That, in fact, that's what I would recommend. So definitely like good content there. One that's not on this slide is Itzikevich, which should be. So imagine here. So there's a very kind of also somewhat kind of textbook level, not so much textbook as this, but like everyone has it, which is a book by Eugene Itzikevich that's called Dynamical Systems in Neuroscience, and is very readable, but has all of the kind of core theory of dynamical systems in as it pertains to things like Hodgkin-Huxley equations, Fitz-Naguma equations, phase planes, the bifurcation kind of fundamentals at least clearly laid out in a relatively concise, readable book. So Itzikevich, Dynamical Systems in Neuroscience, that you could do worse than just, you know, trying to get through that book in about half a year, which is what you guys did, right? Yeah. Okay. Right. And then if there's also some websites and say web-based resources. So if someone was to say to me, "Hey John, I really love this course. What should I do next?" Right? I would maybe say read it, get Itikevich's book, but I would definitely say do Neuromatch Academy. Okay, so this is an initiative that's been running for about 4 years now. Initially it was a conference called Neuromatch, and it was like it had some algorithm to kind of match people's interests. I think that's where the match thing comes from. I think they still use the algorithm, but I'm not sure if that's really the emphasis anymore. But I think the best thing come out of Neuromatch was Neuromatch Academy, which was just it's just a really, really good and like global lecture series course, kind of practically oriented course that has, like, I think fairly, you know, advanced, but also very, very kind of accessible learning materials. And they run it every year in a way that you kind of participate, and you can like be part of the cohort, and you have a group. And, you know, Parza, you've done this, what, more than once, right? Yeah. Do you want to elaborate?
Honestly, it's like, you know, I would absolutely recommend it. The tutorials that we did in the course was inspired by the tutorials that we did in Neuromatch. It's a pretty good survey. It's very condensed. It's not an easy sort of summer school. But I mean, they say themselves that, you know, if you get 20% of the material, that you've done a lot. So great job. So it's not supposed to be like an easy run through, but it actually gives you a very good survey of like what's out there, and it's like very good introductory, kind of like I guess like more than just an introductory, but like, you know, kind of like not dipping your toes, but like, you know, someone throwing you in the pond and kind of like you struggling to kind of like maintain balance. But
yeah,
it's pretty good.
Great. Yeah, thanks, Parza. So I think well, the other ones I've got on this slide, just to wrap up, there is great resources from this organization called the International Neuroinformatics Coordinating Facility. They have sets of tutorials and lectures and so on. For example, there's a lot of virtual brain stuff on there, virtual brain modeling, and kind of multi-lecture series on doing whole brain modeling with TVB. It's pretty good. This is just a self-plug. This is a conference we've run previously in Canada. We haven't been doing it in the last 2 years, but there are 5 years of content of Canadian computational neuroscience research at this website, and I think there's some pretty good stuff there. Scholarpedia is not, it's kind of old now, I guess. Not sure how much it's getting, but it's just it's the best place to see a lot of like fundamental topics in computational neuroscience. Like the Scholarpedia page is the first place to go, right? So if it's something like Hodgkin Huxley or Wilson Cowan or something, you can always do worse than the Scholarpedia page as your like intro to some concept. But yeah, I do think that if you want to decide what to do next and you really want to kind of go somewhere in terms of investment, then do Neuromatch. And yeah, this is just getting to the lecture now. So enough from me. That's it for my wrap up. That's it for my recommendations as requested before. I think we can move into the next phase. Okay, so let's move on to our presentations. I think so. The order we'll do is Mina, Andrew, Shirin, and then from our recordings we have Shivank, Krish, Savannah, and Gabriel. That's all of them.
I think so.
Yep. So 3 in person, 4 recordings that we'll play. Mina, please come take the stage. All right, I wasn't holding the mic then. Hopefully you heard that okay, Sharon, and other people. There's a mic. So on the collar. You can put that in the back, yeah, but it's gonna go be a problem. So I'll wait this a second.
Okay.
Introduce yourself, please.
So I don't really see how do I?
You just gotta get, it's a second screen, sorry. Yeah, it's there.
Here, okay. So am I gonna make it like this?
There we go.
And you can also rotate this so that you don't have to like keep looking back.
Okay, good.
The entire table rotates.
Okay, can Sharon specifically hear me
Sure, does everyone else?
and future audience members? Okay, my name is Mina Rose and this is my cursor. Okay. For the tutorial or the presentation, I decided to dive deeper into the tutorial where we learned about brain synchrony and specifically exploring or investigating how alpha blocking occurs. So this. Oh, because it's this setup, sorry, this setup's. Okay, all right, so just for a brief intro, what are alpha oscillations? So alpha rhythms are oscillations that occur between the 8 to 12 hertz frequency band, and they're associated with they're considered an idle rhythm or associated with inhibition of sensory input, and most commonly during resting state attention. And so a very prominent biomarker that we observe is when we open our eyes, this alpha power decreases. And so if we take a look at the power spectrum when your eyes are closed, we have this prominent peak in the alpha band. And then when the eyes are closed, this peak diminishes or disappears. And so this is because alpha power is being reduced. And this is often observed in the posterior regions of the human brain. And the question is how or what occurs or what mechanism supports this reduction in alpha between eyes open and eyes closed. And we can take a look at that using the Janssen neural mass model, which hypothesizes that alpha oscillations emerge from interactions between excitatory and inhibitory populations. And in this case, this model has an excitatory pyramidal cell, excitatory interneuron, and inhibitory interneuron depicted over here. And it's these, I guess, and the interactions between those populations is what the specific tuning or connections between them is what allows these oscillations to emerge. Specifically, if we take a look here, like if we simulate the activity of this neural mass model, which represents a single node or a cortical region, and we compute the power spectrum, this is what we get, this prominent alpha peak. And we can do this with the code from the tutorial where we simulate the output of a single cortical region and then using and Fourier methods to compute the power spectrum. But in this case, I applied FOOF, which allows us to separate aperiodic background component from the Gaussian peaks to be able to actually see these alpha peaks. And this is what the Janssen model simulates, this alpha peak and along with its harmonics. And so the question from the sixth tutorial and the first task was how can we change the parameters of this model to simulate what happens when we open our eyes, which is reducing alpha power. And we were asked to consider adjusting the following parameters, which is the input noise level, C2, and C3 and 4. And if we take a look at the model, that refers to So C2 would be excitatory input to the pyramidal cell. C3 and C4 would be the inhibitory loop, and the noise level would be input to the pyramidal cells, which not depicted here, but it's an additive term to the excitatory drive to the pyramidal cell. And so to explore this, we use I've set up the manipulations that I'd like to explore, which is varying the noise level, varying C2 between this range, and then C3 and C4, and then running and computing the power spectrum and seeing what we get. And so initially, this is the variations in the noise levels, and what we see clearly is a diminishing of the alpha power in the peak and a slight shift towards increased center frequency as noise levels increase. And we see a similar occurrence in the increasing of the excitatory inputs from the interneuron to the pyramidal cell, where increasing that excitatory input also reduces the peak power, but also shifts it slightly to a higher frequency. And then when we look at the inhibitory contributions to the pyramidal cell, both C3 and C4 show a very similar profile in that the purple represents the base parameter of the model, which is C3 at 0.25. But if we decrease that, so we decrease the inhibitory drive to the pyramidal cell, alpha power is diminished. And if we increase it to 0.3, we get this multiple peaks, what looks like multiple peaks. And this occurs in both the C3 and the C4. And so we also want to look at what the time series, so the output, or how it evolves, how the activity of the pyramidal cell evolves over time, to see if what we're seeing in the power spectrum is because it's driven to saturation, or if it's not actual brain activity. And so we see that this is what it looks like for the noise level, just skimming through it, the C2. It's interesting to see what happens with the inhibitory input, where the lower inhibitory input almost leads to, it dampens the time series to almost no activity, and whereas increasing it causes these non-sinusoidal or non-linear waveform shapes, and this occurs over a much larger time scale, which could contribute to the lower frequency peaks that we're seeing in the power spectrum as well. And then similarly in the C4 as well. And then a step further that I took, which was taking some points from the first tutorial, and that is trying to use phase planes to understand the dynamics between, or how the excitatory and inhibitory connections explain how these parameters affect the alpha power. And so this is the phase plane of why, so the pyramidal activity and the inhibitory activity at varying noise levels. And we see, just like in the power spectrum, what this, I guess, also shows is that increasing the noise level leads to a shorter or a faster EI cycle. And similarly in the C2 ratio, which behaves in a similar manner, whereas the C3, where we saw the non-sinusoidal waveforms, in the phase plane, this shows us that this occurs because it becomes a more wider limit cycle, or a much longer EI cycle. And there's some interesting transitions from being at a fixed point, entering the limit cycle, and then becoming a very wide. And that's observed. And so I do summarize my observations here, where increasing noise level and C2 lead to lower alpha, and that is due to a shortening of the EI cycle, or an introduction of desynchrony, which leads to lower amplitude. But I also wanted to show the relationship between C2 and noise, which both seem to lead to the same thing by doing a parameter sweep of changing both C2 and noise at the same time. And what we see is that at low or moderate levels, C2 and noise have this increase in alpha, but increasing both in either direction or together leads to this diminishing alpha power. And to sum up, what does this have to do with how we keep our eyes, what happens when we open our eyes or close? represents this sudden increase in visual input, which is represented by an increase in noise or C2. And future directions would be using the Robinson-Rennie-White to investigate the limbocortical. Done.
Ina, great job. Questions? Any questions from the room?
I know that in age neuroscience experiments, blinking is involved. And you talked about two states, eye open, eye closed.
Yep.
But when I blink in a high frequency,
Yep.
therefore,
Yes, that's a good question. And it's, so basically this morning we were doing a recording with Dr. Griffiths himself. We were recording his brain sessions while he was opening eyes and opening closed. So basically when your eyes are closed, we don't have that eye blink problem, obviously, right? Because we record a session where your eyes are closed during that time for like 10 or like a minute. And so we don't have the eye blink interference. But then when your eyes are open, obviously you have blinks. And these are usually regressed out or removed as an artifact before we proceed in the analysis of how the power spectrum.
know that in other studies, maybe solid state, maybe whatever, second harmonic
Yes.
has a special role. If you notice that, because it could be that it doesn't play here for some reason, but
Yeah, no, that's a good question. I mean, in the internet, we get the second harmonic peaks quite visibly, but I personally am not sure whether that's because it's a property of the model that we get these second. I know the harmonics occur because they're usually like in brainwaves, you also have non-sinusoidal properties, so you'd get harmonics. But then when we are simulating it here in the model and seeing the effects of diminishing the alpha power in the harmonic as well, don't know if that's because it's a property of the model or it's because it's actually simulating what happens to be able to answer what the role of harmonics are.
I had a question. This picture, here, actually, it's the way you have the model parameters of the red line.
Yep.
Lots of harmonics there.
Yep.
What do you make of that? Why don't you just describe that? What is that showing?
Yeah, so what I interpreted as when we look at the time series, we get the non-sinusoidal waveforms, and when you compute the power spectrum on there, so it's rhythmic, but it has the non-sinusoidal properties, which shows these harmonic peaks, but they're and also starting at a peak at a much lower frequency because of the larger time scale that they evolve.
Yeah, okay, good. See, thanks for putting together. So it's no frequency here, it's 5.
Yeah.
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 1.75 and that relates to that much more.
Right, yeah. So the larger limit cycle, slower frequency, dominant frequency.
Okay, good questions. Any other relatively quick questions for me before we move on?
if so, when you look at the ECG, the age,
Right.
time series is different.
Yep.
And related or not related to this, how you put the noise, how you model the noise. Because about noise, there is many discussions that will always end up with what kind of noise you use.
Mhm.
So noise is actually a major topic.
Yep, and it's one of the topics that we had a lecture on and a slide where it was like sources of physiological noise in the signal. Like you said, like in an ECG or even the ECG, so cardiac noise in neural signal. But then how we model that, there's debate into whether I understand, like in this case, it's an additive term to the excitatory input because it could represent just external inputs because noise is external input. Just a plus this value in this case, in this model.
Randomly sampling from their distribution. Yeah, because I think I think the variance of the Gaussian distribution would be like, representing your amplitude of the noise, or it's just randomly.
Sample from the,
Yeah, the Gaussian distribution.
okay. Final is, do you notice any resonance effect and how can you use it?
It's a good question. So
This harmonics may be emanating from some underlying resonance.
right. So I mean, I guess I'm still confused about the term resonance and how it relates to like resonance of alpha, or so I'm not sure how to use that term, right, or what it refers to.
We also described, we went through like a term of stochastic resonance.
Yeah.
During the courses, which was essentially saying like there's an underlying dynamic. When we add a noise term to the dynamic, it goes up to a certain threshold that we can detect the signal. So it's not necessarily the noise is not necessarily just blurring things out. It's actually making dynamics that are not very salient a bit more salient. So I guess there's like a bit of a confusion of like what do we call as resonance. So in that case, we had actually a tutorial demonstrating the effects of noise. It's stochastic resonance, where how it actually would lead to an improvement of the signal.
Better shut up, otherwise it's still.
No, thank you for the great question.
We need to keep the general discussion like on the wraps, so we do stick the time, but I definitely like the questions, but it's so. Great, okay, Andrew, you as well.
No, it's not. I'm a speaker for everything. There you go.
Okay, hopefully everyone can hear me. So, my name's Andrew. I'll be presenting on the tutorial that we did on Hopfield networks, which is basically a simple model of how our brain can memorize patterns. So, I won't do too much of a background knowledge. Just remember that in the Hopfield model, we have our pattern where each xi is then updated by applying the Hopfield matrix and then taking the sign so that it's either plus or minus 1. And then what we're trying to do is that we're trying to minimize this so-called configuration energy, which looks like this. And then if we have multiple patterns, we can just create the Hopfield matrix by summing up the individual Hopfield matrices. So that's the general background, but now I want to explain the more mathematical aspect of why this seems to work. So let us consider the linear model with no sine functions and with only one pattern. So as you can see here, we just have one pattern, epsilon psi. You can view it as a vector. And then the matrix is simply the rank 1 matrix created by their dot product. And this E that we were minimizing before is actually just the Rayleigh ratio in mathematics, which is also known to be the maximum eigenvalue, and it is achieved at the eigenvector of this maximum eigenvalue. So if we view this using just matrix products, the update rule can be viewed as some projection of applying this matrix with some normalization in the synchronous updating scheme. In reality, we use asynchronous, but for now, let's consider it as synchronous updating. So this is also can be viewed as the power iteration method of trying to find the maximum eigenvector and eigenvalue of a matrix. There are theories that prove that the convergence of this updating rule is like x after k updates minus the true eigenvector is on the order of lambda 2 divided by lambda 1 to the power of k, where lambda 2 is the second largest eigenvalue. With only one pattern, lambda 1 is the norm of the eigenvector, which is our pattern, and lambda 2 is 0. So theoretically, we get convergence in one iteration. And you can see why, because if we apply it, this is just some scalar multiple of the original eigenvector. And with some normalization, we get it in one iteration. So why does this not happen in a Hopfield model? It's because we do asynchronous updating. So we have to do multiple steps. Number two, the diagonal of the matrix is set to 0, which complicates a lot of things, but is needed, which I'll explain later. And number three, the normalization of this sign function is very nonlinear, and it maps it to this very non-smooth, not even connected domain. In the original matrix formulation, we're just projecting it onto the unit sphere, but here we're projecting it to the corners of the unit cube, which of course is not connected. And the problem becomes even worse for multiple patterns. If we have two patterns, xi1 and xi2, if we add their matrix together, the eigenvectors actually don't match. And this corresponds to the crosstalk term we talked about in class. The only time they match is if the two patterns are completely orthogonal. And in neuroscience, you can think about it as if I'm trying to memorize two very different things, I can memorize it perfectly. But if there are two very similar things, it becomes a lot harder and sometimes impossible. So this clearly doesn't work with the matrix model. So how does Hopfield deal with this? Hopfield does this by basically asking three questions. Given an operator, what's the only information it knows? And the answer is the spectrum or the eigenvectors and eigenvalues. So how does power iteration give us the correct eigenvector if this summation has changed it? Hopfield does it by using the sign operator that normalizes everything so that every eigenvector remains an eigenvector even after addition. And finally, what happens in the limit? If we add more and more eigenvectors, what happens? Well, and this is one of the questions from the tutorial. Basically, if you have an n by n matrix, the most they can memorize is n vectors. And through our normalization, every vector remains an eigenvector, and they all have eigenvalue 1. So by applying this operator multiple times, we should converge to the closest eigenvector. Yep. So if we do that, I've changed a few things here. First, I do asynchronous updating, but I don't make it random. And two, I change my flip fraction to be 0. And I get some interesting results, which is even with a 100 by 100 matrix with 300 vectors I'm trying to memorize, I still seem to recall it perfectly because I haven't flipped anything. But if I apply it more and more, I somehow spontaneously jump out of the correct local minimum and travel to another one. In terms of neuroscience, maybe it's like by overthinking, you get the wrong answer. But it's surprising that it converges to something that's around 0.6 to 0.7 correctness rate. By adding so much vectors, I'm basically creating a random matrix, and every point on my vector is either plus or minus 1. So if everything is purely random, I should get around 0.5 accuracy. But here I converge to 0.6 to 0.7. Reason why this might be is because we're diagonalized. The diagonal of our matrix is set to 0. This makes it not completely random. And also, and I think that's the main reason why I can think about it. Otherwise, I'm not too sure as well. And that's all my results. Thanks very much.
That's very, any questions?
Mhm.
So I think, you know, I'm interested in the things, the stuff you looked at the start,
Mhm.
and also the comment you made about kind of going from like a unit circle to the corners of the sphere, being the effect of the sign
Yeah.
term in the hot field network.
Mhm.
So, like, I think there's a geometric description of that, but like, what else is there to say about
The wires.
transformation?
Yeah. So the unit sphere is very nice because if you have a random point in space, unless you're at the origin, there's only one closest point on the unit sphere if you project on it. But for unit cubes, or specifically corners of the unit cubes, now given any random point in space, you could be equally close to 2 points on the unit cube, which makes the projection a lot worse, which I think is what explains some of the random spontaneous movement in the figure I also show.
So kind of sign flipping.
Gives like a, yeah, it gives a non-unique projection.
This is a tricky one. No idea how to figure it. Every time there is projection,
Mhm.
some information is lost.
Yes.
Can you read it?
Probably not. For example, this is only dealing with discrete cases, right? The brain probably memorizes an infinite number of memories, possibly uncountably infinite many. So at that point, is your brain, if you do it like this, it's almost impossible to kind of find every single eigenvector well. Another potential way they do it is they keep it, maybe the brain has some way to still have every memory have a distinct eigenvalue. And then there are like ways in linear algebra where we can find like the third eigenvalue or like the 100th eigenvalue. But we're not sure if the brain has the complexity to project away the higher eigenspaces.
That's the. Oh.
Yeah.
Wonder, this is done by having many eigenvalues?
No, so this is using Hoffield's model where everything is normalized to have one as eigenvalue.
So between those bars,
Yeah.
is it possible to calculate correlation?
Maybe.
This correlates to this, look at this series of correlations.
It could be possible, but
Maybe teach us.
maybe. But I think another reason why there might, yeah. Another thought I had about why this is like kind of spontaneous, like or like random, is because sometimes if you do the matrix dot product, you're just adding ones and negative ones, and it gets to 0. But on a computer, you have numerical instability. 1 minus 1 is not 0. It's like plus minus 10 to the negative 20, and that might cause some spontaneous changes as well. So if with perfect precision, I think we might have some correlation, but on a computer, I don't think we can get any.
I have one final question. So the part that earlier on when you talked about the like ratio of eigenvalue 1 eigenvalue.
Yes. Yes.
So yeah, can you give me kind of intuition on here? Like, what is this? Why is that relationship, you know, approximated by ratio of the first eigenvalue?
So it's basically like when you apply the matrix to a vector, you can decompose the vector into the eigenspaces. So when you apply it, you're basically multiplying each part by the corresponding eigenvalue. If you normalize it correctly, you're basically you're multiplying everything by lambda k and then dividing everything by lambda 1. If you apply it enough times, the lambda 1 term dominates because all the rest are like smaller than 1. So then the rate at which the other terms go to 0 is dominated by how fast the second term decreases to 0, which gives us the lambda 2 over lambda 1 ratio. Yeah.
So that's the rate at which the first eigenvector
Yeah.
the rate at which it comes to dominate the matrix
Dominate
is
the result of the dot product, I guess. Yeah.
that rate is
Yeah, so like once you find the first eigenvalue, people can like kind of project it out and then find the second one. And then the second one, the rate will be determined by lambda3 divided by lambda2.
okay. Okay, so Sharon, you're up next.
Thank you.
What I've been doing for folks in the room that you may or may not have heard is like wave my hand when you get to 7 minutes. I've actually been doing 8 minutes rather than 7, but I think that's fine. So in other words, I've waved my hand at 7, and then you've got 1 minute left. So yeah, if you can see that, then there you go. That's your signal for.
All right, I probably won't see that because I'll be sharing my screen, so I'm just seeing my own screen. But if you can take the mic and you can just say 6-7 minutes, and then I'll hear you. But I may not see you because I'll be looking at my screen. If-
Keep an eye on the time. That'll do as well. Okay.
Okay. Can you hear this?
Yes, I can hear you.
Okay, right. So I'll
There-
just say when you're at 7 and then you got 1 minute left, okay?
All right, perfect.
Can we? Yeah, can
Uh,
you share your screen and then we'll bring that up?
Sure. But it says someone else is sharing, so
Yeah,
if,
we'll pull. If you can do the share, then we'll pull it up. Do we need to stop sharing first? Yeah, it's good, but it's there, right? It's like hiding.
Mm. Oh yeah, I can share now. All right. Okay, can you see? Can you see my screen?
You see it? Well, nearly. Yes, we do.
All right. Okay. So I'm going to talk about an exercise from tutorial 8 on noise and noise-induced transitions between attractor states. And in this tutorial, we talked about 4 different ways in which noise can be useful or the role of noise in the brain. I'm just gonna focus on the third one. And if there is time, maybe there won't be, but if there is time, I have worked a little bit more on this and actually modified one of the equations to think a little bit differently about noise as not just something that the brain takes and randomly uses, but something that the brain modulates itself and like kind of like a currency to balance entropy or uncertainty in brain. So that's a kind of model I've been working on. If there's time, I'll show you something on that too, but otherwise that's okay. All right, so let's look at this. What are noise induced transitions? Again, I thought of it in terms of an analogy. Imagine that you are driving a car on a road, and if there is bifurcation, meaning that the road is splitting, forking, if you don't have noise, if you don't have these like little bumps on the road, you'll just go left immediately when there is a turn. But if there are some bumps, which we think of them as noise here, then you are kind of being nudged to left or right even before that turn actually comes. And somebody looking at you may think that you've already made your decision, but actually these bumps are kind of helping you to explore all, I mean, both sides of this landscape. And then we have these two equations here. Basically, one of them, the first one, is telling us how the state or the system is like evolving in time, and then the other one, I mean, how this transition evolves in time, if I'm not mistaken, and then the other one is the stationary equation, which tells us that where does the system tend to want to stay, and then both of these are shaped by how much noise we have. So we're gonna look at some simulations. This was really fun to do. Let's look at here what we have. Oop. Yeah, so we have some widgets here. We can change the bifurcation parameter and the noise value, and then see what happens if I can find the, well, let's look at what we have already here. Yes, we have system trajectory with adaptive noise. Oh, wait, is that my thing? Oh, sorry, I went too far back. Noise induced transitions. Let's see. Okay, let's look at this one. So the first plot is showing us that we have the bifurcation parameter at 1, and at 0, if it's lower than 0, this mu parameter, then you have stable system. Even if it's over 1, you have a bistable, so you have 2 stable points, and here it is 1, so we have 2 stable points, and then we have a little bit of noise, 0.2. So we see that the state is going like wiggling, and then if there's like noise, and then it's a good timing too, according to the oscillations, then you get like a really sharp downturn. So this is, and then you have the histogram for the simulation. This just shows us how much time the system is spending in each of these states. And then you see these valleys and the hills. Again, imagine that your car is going, and then if there is a hill and there is no noise, then it's not gonna, have energy to go up that hill and cross over to the other valley. But if there is enough noise, then it's easier for it to go there. And then if we change these values, we see how, I don't see the widget here, but let's look at another one. We have another simulation here. Oh, here is the widget. So see, we have here the bifurcation parameter is at 1. That means that we have 2 stable landscape, 2 stable point landscape. Let's make it a bit higher, and we see we get deeper valleys. Let's rerun this. Oh, it reruns itself, so I don't need to do that. Where did it go? Okay, so let's put it at, you see now the values are deeper and our noise level is still the same. So it's maybe not as easy for the system to switch between these states. these points. So let's kind of increase the noise by quite a lot. And then we see here that the system can transit between the stable points easier. And then we have also, this here some other parameters, but I want to show you the heat map. This is just another way of showing this happen and how this happens. Here we have the noise level at 0. So as you can see, the car is just staying in one valley, it's not going anywhere. But when you increase the noise a little bit, then you see that it starts to explore both sides. And if you increase it even more, do you see it becomes almost like more continuous? It's exploring a lot more of this landscape. Then what do we have here? Yeah. Oh yeah, this is just shows us how much time it spends there. So it's kind of similar to the other one, but it's over time, if I'm not mistaken. Yes. And we can change the values here and see basically the same things happening. And then these are the answers to the questions. It's basically exactly what I just explained, so I'm not gonna go through it. But if I have time, can I show you what I've been working on? How much?
Yeah, 30 seconds.
How many? How long?
30 seconds.
Oh, okay, then forget it. But
but
it's in the tutorials. I mean, it's in the notebook, so you can look at it later.
Definitely interested to hear about this, Sharon. And maybe there'll be time to take a look later, or we can talk about it like offline. Let's have a thank you and report, Sharon.
Thank you.
Questions from the room?
I think you established in what I've seen, something that is known, that with the noise, we can get the signal better. We can discover the signal when we increase the level of noise. But this a little bit contradicts the signal to noise ratio. So if I increase the noise, the SNR goes down. So what do you think of it?
What? It's a little harder to hear you because it's from the.
Let me do that. It works. Do you hear me?
Yes, I hear you perfectly now.
Better now? Okay. So you established that when you increase the noise level, before we didn't see the signal, now we see the signal because you increase the noise, right?
Actually,
In
no,
the
that's.
last few, yeah.
I think that's another simulation where we see how noise can help us detect the signal. In this one, it was showing more in terms of noise-induced transitions between fixed points. But also, I guess, like it does in a way help you to to detect the signal at the same time better as well, because that's what noise does in general. So that's one aspect of it. But I'm not sure if that was the focus of the simulation, but I might have missed that. But
we
in
do
any case, what
simulation
was
to
the
learn something. We learn from simulation, right?
It is, she demonstrated that in presentation, but in one part of the tutorial that we didn't cover was actually explaining the question that the very question they posed. And what we see is that as we increase the noise term, the noise, we see kind of a curve happening in terms of like the synchronous noise ratio, detectability, where it peaks at a certain level of noise, but then it comes back down as we increase it. So like it has like a sort of linear response as we.
Because the ratio goes down.
Yeah, exactly. It goes up first and then comes back down. So it's better.
Any other questions on the presentation? in the room? So I actually want to maybe invite you, Sharon, to actually pick up where you left off and tell us a little bit about what the last bit you were going to say, because I am quite interested in that. And we do have a bit of time. So what I, but
So I'm
that's like, yeah, I know you want to show us as well. So let's hear from you a little bit about that. Then what we'll do, guys, we'll take a break. And then I guess Mina and Andrew, if you want to take off at that point, that's okay. But Pazra and I, and we're gonna kind of keep going and grade the videos and play them for the Zoom call as well. So we'll keep going, but we'll hear from Sharon a little bit, then we'll take a break, then we'll be playing the recordings from the people who weren't able to make it today, and that will take us up to 5 o'clock. Okay. What do you got?
All right. So remember during the probabilistic brain, I had a question about how does the brain transform continuous input, sensory input to discrete perceptual categories or decisions. And I've been thinking about that and working together with my research buddy, GPT-4o, and came up with this kind of a unified model where different, so it's called like a hierarchical oscillatory attractor model, or HOME. And I'm working on a paper on it too. I can share it with you when it's work in progress right now. But one of the things that this model kind of suggests is that noise is not just this random, like the Gaussian noise term that we just add, and it's quite arbitrary in a way, but actually maybe different, like the brain itself uses noise as a kind of currency to modulate noise. So when uncertainty about input is quite high, so that's like an entropy, and this is in the sense of Shannon entropy in information theory. It's not the entropy in thermodynamics as a sense of disorder of the system. It means uncertainty. And if uncertainty is really high, then it allows so different oscillatory gating mechanism or function allow more noise to go up the hierarchical layers, and then allow for better. So we saw how noise is useful, but it just shows us how it can actually the brain, how can it use it more meaningfully or more like actively as opposed to passively. And then so when entropy and uncertainty is high, and then the brain can and especially the alpha wave can allow this noise to be gated and like open. So we have like a gating mechanism for noise itself. And then let me show you the equation here. Can you see I'm using dark mode, so I don't know if it's visible to you. Maybe I can yeah. So this is like in the model, sorry, the equation that we have in the course. And you see that this noise term here is not very dynamic. So if we add here, so the rest is the same as we had. So the bifurcation parameter, it pushes it forward, and then like it's a backward pull, and then you have here this psi of t, which is the like a noise power kind of term, and this is then defined here below in terms of this h of d is the Shannon entropy, and then this g of I of t, this is the gating function, the oscillatory gating. So these together, when you put this in the equation, now here you don't have just noise, this randomly is there or is not there. Now you have like this modulated. And then I kind of worked on a kind of like a toy code to see if we can simulate this. Now I have to minimize again so you can see. So if you see here, it's a little bit more like it's different. I have no idea if this would match the actual experimental scans or data. But also another thing is that in this model or in this simulation, the entropy is arbitrary. I just put a value for it in there. So the system is not actually counting, you know, it's not managing a real entropy. So I'm telling it, oh, now entropy is, so our uncertainty now is high, and then the noise is modulated based on that. It's not doing that on its own currently, the simulation, but that can be done too. I didn't have time to extend it that much. But then here you have this kind of system trajectory with adaptive noise. And then you can see like maybe here the uncertainty is high or low, and then you have these wiggles become different. And then here also you have the oscillatory gating that allows noise to be on and off, and then this how much time the system is spending in each state, attractor state, based on this kind of understanding of the noise. So here I'm explaining it more. But yeah, that's like the basic idea is that maybe noise is not just this, you know, random and passive thing in the brain. Maybe the brain, maybe the brain is actually modulating it as well. And that helps us understand a little bit more maybe how the brain transforms continuous sensory data into discrete perceptual categories by using noise as a kind of currency for making decisions or negotiating, you know, when something needs to be discretized or when, you know, uncertainty is high and we don't know, we don't have that fixed point. And also, I don't know if that has been, so far as I've done research, I haven't seen this being interpreted in this way, but you know, I'm very new to this field, so I might be wrong. So thank you for listening to me.
Yeah, thanks for that, Sharon. I mean, a lot there. Like, I guess, one or two comments and questions that come to mind, but there's a lot to kind of chew on from what you put together. But yeah, what you were doing there was you were kind of defining like a time-dependent noise and I think a state-dependent noise as well. And then I think in terms of just making some connections to things we talked about, and I think some of the ideas you're thinking about. So, like, what would time-dependent noise look like from a cognitive neuroscience point of view, right? I think if you go back to the probabilistic brain lecture, you know, which I think is what you're basing all of this on, but just think about you know, agent moving through environment. The environment has variable levels of information, right? Like sometimes I know this is extending a little bit beyond the that like specific dynamical system model that you've got there, but I think in terms of like broadening the interpretation out, like sometimes environment or sensory input or input has high levels of uncertainty and sometimes it has low levels of uncertainty, right? So maybe insofar as your noise term there was like a time dependent noise term, that I wasn't quite clear like how it was being modulated over time, what was kind of defining when it goes high and low. But if that is something that could be, you know, externally driven, right? That would kind of make sense, I think, in terms of what the I think the kind of concept behind Bayesian brain, probabilistic brain, a lot of predictive coding as well is exactly that. It's like it's not necessarily it's that sometimes there's more information available in your sensory input. Sometimes there's less information available in your sensory input, and in the times when there's less, then you kind of need to lean back on your other information, your priors a little bit more. But that's something that if you think about instances of that, the 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 standard deviations, right, of the input distributions as being like sometimes wide, sometimes small, your evidence inputs, then your likelihoods, then and then just think about that as being like continuous in time. You're kind of constantly sampling. So that would be that's how I'm kind of thinking, like seeing connections between this idea of like a time dependent noise and maybe a kind of more general idea about kind of Bayesian inference from a cognitive perspective. So just riffing on your ideas there, really. But my question as well at the start of all that was like, how are you defining the time and the state dependent noise? Is it coming from the system there, or is it externally driven?
Oh, that's such a great question. In this simulation, it was externally driven, so it was fake, basically. But in the actual model, the home model, it comes from the oscillations, and so it's internal. So it's the internal brain clock, and it's something that I have explained. I have worked on it in the paper. If you don't mind, I can send you the paper, and I would love to know what you think about it. But yeah, it's completely internal, so it's not coming from outside. This time, it's a kind of dynamic relationship between the hierarchy of the different brain waves and the oscillations. So they kind of work together, and then you have like this gating mechanism for noise. But it's a bit hard for me to explain it orally because again, I'm still exploring myself, so it's not like it's an established. It's just some ideas. But
Right.
in the paper, I can explain it a bit better. But basically, what it's trying to say is that on some layers, like a hierarchical levels and the layers in the brain, when you have, say, continuous in sensory data that is very uncertain, like what is it? Is it a face I'm seeing, or is it like, I don't know, is it a moon, or what is it? So you don't know. And then as you kind of pass on information um, up up these layers from different, let's say like delta to alpha and higher up, then it becomes more and more discretized or discrete. And then noise has a role in this. So noise is not just there randomly appearing and the brain passively being influenced by it or just using it. The model is trying to say that these oscillations gate noise itself. So they can understand like when they need more noise to kind of make a decision. So when there is like time to make a decision and sensory data is uncertain, then it allows more noise to pass to different layers and to enable that like decision making. And when there is like, let's say for example, when you're dreaming and this exercise on the alpha wave when you have your eyes closed and open, that was super interesting because when you're dreaming, everything is kind of how do you say, like almost like AI, like, right? First it's like a train, then maybe it turns into a tree, and then, you know, there's a cat, but then there's a face. So you don't have that kind of discrete function, and it's kind of interesting that during like REM sleep, alpha waves are suppressed, like you don't see them, because in this model, the alpha waves are very important, have a very important role in negotiating noise and how much it should pass on to help making decisions. Does that at all answer your
Okay.
question, or does it create more questions?
Yeah, that's super interesting. I mean, you had like a 7-minute assignment and you kind of came back with the master's thesis. So
Oh.
I mean, interesting, but like probably more than we can cover here. All right. So I think, were there any other questions in the room? Nothing burning? Well, okay. So let's, that's a wrap for our live talks. We'll take a break. We'll reconvene in 5 minutes, and we will screen the recorded talks that we have, and then we will conclude the day and we will conclude the course. So see you back in 5 minutes.
Shirin, do you hear me?
Hi, yeah, I can hear you.
Yeah, okay. So you use thermodynamics terms there, and you even say thermodynamics. So temperature is a major parameter in thermodynamics, right? Can you relate temperature fluctuations to noise?
Yeah, so that's actually a really good question again, because noise in thermodynamics comes from like overwhelmingly from heat, from temperature, and that adds to the disorder of the system. So for example, in quantum mechanics, if you want to keep coherence or entanglement for longer, then you need to have like literally zero noise, zero temperature. That's why like quantum computers have to be extremely cold.
Exactly.
And then so that's kind of noise in thermodynamics in relation to quantum mechanics and things like that. And an entropy here in thermodynamics is a measure of the disorder of the system. So when you have more noise, you have more like probabilities kind of go crazy, and you have basically chaos. Whereas in information theory, noise here is actually information. So it's like sensory data, like something you see, like it's not heat, and also it doesn't necessarily mean disorder. It just means uncertainty. So this is like an information theoric interpretation of noise and entropy. And this entropy I'm talking about is the Shannon's entropy, and it has an equation for itself that I added to our existing equation to make this noise kind of dynamic. So yeah, these are just the same name, the same words, but they mean different things. And then, of course, in the brain, you have no heat as well. And one of the like side questions is that some people say that the brain is like quantum, and then others say that, well, if it's quantum, then how can it be so warm? So yeah, maybe in that sense you can link these two, but otherwise, these are different interpretations of noise and entropy.